Hello everyone, it's Angela, and today we're going to be going over problem 1 on your pre-Tuesday workshop regarding combustion. Now, as I read the problem, we're going to be highlighting the important information. So, we have that a 13.1796 milligram sample of a new pure compound is completely combusted in pure oxygen to produce 0.03668 grams of carbon dioxide and 4.5038 milligrams of water and no other compound. And the question is overall asking for the empirical formula of this new compound. Now, for combustion problems, we use the bubble method, which is a visual representation that makes it easy to see what we should be doing, what's going on, where we should be going. Now, the combustion problems have a general formula, and so let's just see how we get there. We know that the sample is making CO2, carbon dioxide, CO2, and water, H2O. We know that it's combusted in pure oxygen, so I'll write that here. And you may think that we don't know the atoms in our starting sample, but if we look, we know that we produce a C, an O, and an H. So we know our starting compound also needs to include these things. So I will write it down, C, H, and O. And we don't know the subscripts right now. We're trying to solve for the empirical formula. So I'll write that down as X, Y, and Z. So let's go in and input our data. We have the starting amount of the sample, 13.1796 milligrams, the starting amount for CO2, and for H2O. Now, the initial sample and CO2 are both in milligrams. Combustion problems are best worked in grams, so let's convert them from milligrams to grams using our conversion factor of 1 gram per 1,000 milligrams. Now, after this, let's focus on CO2. We want to go from grams of CO2 to moles of CO2, and we do this using the molecular mass. You can solve for the molecular mass of CO2. It is 44.01, so we use that conversion factor to get moles of CO2. For this overall problem, we're going to need the moles of C at the end. So let's solve for it here. In CO2, we have 1 carbon per 1 CO2 molecule. Therefore, the ratio of CO2 to C is 1:1. And so you can solve for the moles of C. Now we need also the grams of C. We use the atomic mass of carbon that can be found in our periodic table. So we can use that conversion to overall get the grams of C. Now we'll do the same thing for H2O. We need to go from grams of H2O to moles of H2O using the conversion factor of its molecular mass. We need to solve for the moles of just H in H2O. There are 2 H's per water molecule. Therefore, the ratio of water molecule to H is 1:2. So let's use that to get our moles of H. And now we need our grams of H using the atomic mass of hydrogen. This is found in our periodic table. So this is our final answer for grams of H. So we have grams of C, grams of H, the initial grams of the sample. If you subtract these two numbers from this initial sample, you will get the grams of oxygen. So let's do the subtraction to fill in our bubble and get the grams of oxygen. And now we really did that so that we can get the moles of oxygen. So let's use our conversion factor, which is the atomic mass of oxygen found in our periodic table. So we will get that this is the overall moles of oxygen. So when we're rewriting we're solving for our empirical formula, we're going to take this X, Y, and Z and input the molar amounts of C, H, and O. So let me do that. All right, C, 0.00083334, H, 0.000500035, and then O, 0.0001665. Now the next thing that you want to do is divide by the smallest molar amount. If you look, that is oxygen, so we'll divide each of these numbers by 0.0001665, and when you do that, you would get that C has a subscript of 5, H has a subscript of 3, and O will have a subscript of 1. And this is our final answer for the empirical formula of this new compound. Now, that is our video for today. I hope you found this helpful as an introduction to combustion. Thank you so much for watching.